Today, I'll be giving a presentation on graph convolutional networks, which were proposed in the paper seen here, Semi-Supervised Classification with Graph Convolutional Networks, by the authors listed here. The main idea behind this paper is that convolutions work very well for things like images and 1D text sequences that have fixed structures. However, it's not trivial to generalize these operations to graph data. So, this paper generalizes the convolution operation to graph structured data. The authors then use the convolutions that they create and stack them with intermediate activation functions to form high-performing models for semi-supervised node classification on graphs. Prior to understanding graph convolutional networks, it's useful to get some background on general graph theory and graph signal processing. And the first important concept within this area is the shift operator. The shift operator can basically be thought of as a matrix representation of your graph. So generally, you're given some input signal x, which you could think of as a value assigned to each node in the graph, and then multiplying x by the shift operator equates to basically diffusing this signal through the graph, or aggregating the values of your neighbors. Some examples of shift operators include adjacency matrices, which basically are matrices that represent the graph connectivity. One useful thing about these is that if the graph is undirected, these are definitely symmetric. You also have the Laplacian matrix, which is defined as the difference between your diagonal degree matrix and your adjacency matrix, but this is only defined for undirected graphs. But one useful property of this is that this matrix will always be positive semi-definite, which tells us that we have an eigendecomposition with all positive and real eigenvalues. You could also use different normalized adjacency and Laplacian matrices seen at the bottom, which basically multiply your Laplacian and adjacency matrices by your degree matrices. Another useful concept is the graph Fourier transform. So given our shift operator, which could be our adjacency matrix, the Laplacian, one of the normalized variants of these, and so forth, we can derive an eigenvalue decomposition for this matrix given that it's normal. And this eigenvalue decomposition or diagonalization can be seen here. Here, the V matrix represents all of the eigenvectors for our shift operator, lambda represents the eigenvalues for our shift operator, and then V to the H is basically the conjugate transpose of our eigenvector matrix, which you could think of as an inverse, but an inverse that applies to matrices with complex values inside of them. Given this diagonalization, we could define the graph Fourier transform as seen here. Basically, we take the conjugate transpose of our eigenvector matrix and multiply it by our input signal x to yield our Fourier coefficients x double prime. Similarly, we can apply an inverse graph Fourier transform to get our input signal back by simply multiplying our Fourier coefficients by the eigenvector matrix, which is just the inverse operation as the graph Fourier transform. But why does this matter? So assume that we have a filter encoded by a matrix H that we want to apply to our graph. Generally, what's assumed inside of graph signal processing is that this filter, matrix H, is a polynomial of our shift operator. And what this means is that it could be written as follows. As can be seen here, this basically implies that our filter would then have the same eigenvectors as our shift operator. And then the eigenvalues would be some multiplied function of the eigenvalues of our original shift operator. So what happens when we actually multiply our input signal by this filter? We can see that it reduces to the operation seen here. And basically what happens is we apply the Fourier transform, apply a pointwise multiplication encoded by the eigenvalues of our filtering matrix, and then apply an inverse Fourier transform to get our output. In other words, the application of this filter actually decomposes into something that is pointwise inside of the Fourier domain. Now that we have some simple background in graph signal processing, we can actually formulate the problem that's addressed by the graph convolutional network paper, which is graph node classification. More specifically, it's semi-supervised classification over graph nodes. So within a graph, such as the one seen here, We assume that some of these nodes, but not all of them, are labeled with some kind of label. So we apply semi-supervised classification over the nodes because not all of them have supervision and not all of them have labels. Each node inside of this graph has some kind of input feature, which could be thought of as just some input vector associated with each node. And our goal is to take these input vectors assigned to each node, as well as the information encoded by the graph structure, and then use this information to input into a model that can correctly classify nodes within our graph. Many approaches to semi-supervised node classification preceded the graph convolutional network. All of them still assumed that only a portion of our nodes were labeled, but not all of them. One of these approaches used explicit regularization to smooth label information across the graph, which was needed because only a portion of labels for nodes were provided. And this was encoded by the equation seen here. Basically, what this loss is saying here is that we take a supervised loss over our node classification, which could be just a normal supervised loss such as cross entropy, and then we add to it a regularization loss that is weighted. And this regularization loss basically takes the output of our model and multiplies it by the Laplacian matrix, seen here. And what this does is it basically punishes the model or increases the loss when adjacent nodes have labels that are different from each other. So this is actually somewhat limited because it assumes that nodes that are connected are likely to share the same label, which is not always the case. Some previous methods also used neural networks for graphs, but these were usually RNN-based approaches and they had several issues, such as requiring different weights when the nodes have different degrees within the graph, having too high of computational complexity because the RNNs are sequential, or requiring some kind of ordering over neighboring nodes to be induced. So we want to move away from this previous model towards something that's more expressive. And to do this, the authors present the forward propagation rule seen here, where we linearly project our node features and then multiply them by the product seen here that's pre-computed as the product of our augmented adjacency matrix and diagonal degree matrices. And then we apply some kind of nonlinear transformation to yield the node features of the next layer. So this forward propagation rule can be efficiently implemented with sparse dense matrix multiplication, but the authors spend a significant amount of time motivating and deriving this rule. And their argument basically says that this rule can be seen as an approximation to a spectral graph convolution. So if we consider a spectral graph convolution given by the expression seen here, then we can notice a couple of things. First of all, this convolution includes the U matrix seen here, which is the eigenvector matrix of our Laplacian. Now, why is this? Well, it's because when we do this convolution, we're multiplying x by some matrix that's given by the diagonalization seen here. And we know that we always assume that this matrix is going to be some polynomial of our shift operator. It's going to be a polynomial of our Laplacian. Therefore, it shares the eigenvectors of the Laplacian, and we can just parameterize it with this g of theta, a diagonal matrix that is some function of the eigenvalues of our Laplacian. The only issue with this is that we can't actually implement graph convolutions like this in practice because it's too expensive. It involves computing the eigenvector matrices of our Laplacian, which can be very prohibitive for large graphs. So we need to find some way to approximate this operation. The authors pull upon some previously shown results to create an efficient approximation to the spectral graph convolution. Namely, they represent the diagonal g of theta matrix, which is used to parameterize the spectral graph convolution with a truncated Chebyshev polynomial expansion. And if you're not familiar with the Chebyshev polynomials, I've added the recursive definition of them here to help out. So basically, as seen in this expression here, g of theta can be represented with this truncated Chebyshev expansion. And as you see, this is a kth order expansion, so we take the Chebyshev polynomials up to order k, and each of these Chebyshev polynomials is parameterized by the eigenvalues of the Laplacian matrix. And the exciting thing about this is that we can then substitute this approximation for g of theta into our original expression for the graph convolution to yield the expression seen here. And basically what this tells us is that our spectral graph convolution can be approximated with a kth order Chebyshev polynomial, where each term of the Chebyshev polynomial is taken with respect to the Laplacian. And the interesting thing about this expression is that the U matrix is actually completely removed, which follows directly from the simplification of the degrees of this diagonal matrix right here. And the exciting thing is that we can then take this approximation to the spectral graph convolution, seen here, and we can evaluate this in linear time with respect to the number of edges in the graph. So it's significantly faster than the formulation we saw previously for the spectral graph convolution. So we've now simplified this spectral graph convolution with the approximation that is just a kth order polynomial, which means that our spectral graph convolution only depends on k-hop nodes for a given node. However, this simplified approximation still does not give us a forward propagation rule that we've seen before. To do this, the authors assume that we take k is equal to 1. So we assume a polynomial approximation that is linear with respect to the Laplacian. And this actually ends up not being an issue because we can stack these linear layers and separate them with nonlinearities to create a richer class of functions. So with a few assumptions to this linear approximation to our spectral graph convolution, we can simplify our previously shown expression into the one seen here. So this is much closer to our forward propagation rule, but the issue with this is that the eigenvalues of this matrix seen here, the identity plus the product of the degree and adjacency matrices, are between 0 and 2. And if you're familiar with spectral analysis, you know that if we repeatedly apply this operation to our graph signal, if our eigenvalues are between 0 and 2, we can have problems with exploding or vanishing values. So to avoid this issue with our eigenvalues, they introduce a reparameterization trick as follows, where we take this sum of the identity and then product of degree and adjacency matrices and replace it with our augmented adjacency matrix, where we take the adjacency matrix plus the identity matrix and then multiply this by the diagonal matrices to form the product seen here. And after we introduce this normalization trick, we actually get the forward propagation rule that was seen before, where we linearly project our node features and multiply it by this pre-computed product of our augmented adjacency matrix and diagonal degree matrices. So we now understand that the forward propagation rule of the GCN is just a first order approximation to a spectral graph convolution. But because this is a first order approximation, we have to stack these operations on top of each other. So we have to continually transform the node representations, aggregate the neighbors, and apply an activation function. And by stacking these operations on top of each other in between activation functions, we can represent a richer class of functions with the GCN. Some of the pros of this newly proposed GCN are that it no longer biases connected nodes to be classified the same. It handles all possible node degrees with only one weight matrix per layer. It can perform semi-supervised classification by just evaluating loss on the labeled nodes and performing optimization with some gradient descent algorithm. And it is also extremely efficient compared to the previous spectral graph convolution representation that we saw. And we can basically summarize this with a two-layer graph convolutional network seen here. And as you can see, we take this adjacency matrix, which is normalized with our degree matrices, and we linearly project our node features and multiply it by the adjacency matrix, which equates to linearly projecting the features and then aggregating neighboring features. And we apply a ReLU to this, so this is our nonlinearity. And then we perform the operation again. We simply take the representations derived from this first layer after the ReLU operation, and we linearly project them and then again multiply by the normalized adjacency matrix to aggregate the representations of our neighbors. And after these two layers are complete, we perform a softmax operation to yield a probability distribution that can be used to classify each of our nodes. The GCN is evaluated empirically on several well-known semi-supervised node classification datasets, and they're listed in this table taken from the paper here. These datasets include CiteZero, Cora, PubMed and Nell, which are well-known semi-supervised node classification tasks for graphs. The only limitation of these experiments is that the authors don't consider any transductive classification tasks, which means that you don't ever try and classify graphs that you do not know the structure beforehand. You never try and classify a graph you haven't seen before. And if you think about it, this makes sense because in our forward propagation rule for the GCN, we have the adjacency matrix inside of it. So there's no way that we can forward propagate without knowing the structure of the graph. Therefore, this method can only apply to transductive classification tasks. For all of these experiments, the authors use a two-layer GCN. However, in the appendix, there are some experiments with deeper networks up to 10 layers. The GCN is always trained with batch gradient descent, which equates to just feeding the entire graph through the GCN at each iteration. And when you look at the performance of the GCN across the various experiments, it actually sets the new state of the art on all the tasks that were considered. So the GCN is compared to several other propagation methods that were previously proposed, and it performs quite favorably. In addition to this, the GCN computation time, or the time that we take per epoch, is shown to scale linearly with the size of the graph. And when you look at the times per epoch listed here in the table, we see that not only do we improve performance over some of the previously used methods, but we also significantly decrease the computation time, usually around 3 times from the previous method planetoid listed here. Despite the impressive performance of the GCN, there are still several issues that have to be solved. Primarily, we need some way to deal with directed and weighted edges. The current GCN model assumes an unweighted symmetric adjacency matrix, which means that we can't have graphs that are directed and we can't have edges that are weighted differently from each other. In addition to this, the GCN has somewhat unreasonable memory and compute requirements. Because we train it with batch SGD, we need to fit the entire graph into the GPU to perform an update, which is often not possible for large-scale graphs. Although we can decompose the graph into subgraphs, what we'll see is that the receptive field for each node actually expands exponentially at each layer of the GCN, which still creates memory and compute requirements when we try and compose subgraphs. And this is a problem that's explored by several follow-up papers. We also cannot generalize to unseen graphs. The GCN is only evaluated on transductive tasks, and we never try and evaluate it on unseen graphs or inductive tasks. And finally, the self-connection that we use within the GCN is weighted the same as the neighboring connections. So if you remember, within the forward propagation, we use this augmented adjacency matrix where we add to the normal adjacency matrix an identity matrix. But it's not the case that we always want to add the identity matrix to get our augmented adjacency matrix. It's possible that we could scale this identity matrix in order to control the weight of the self-connection compared to the weight of the neighboring node representations. And with that, I want to conclude this presentation on the graph convolutional network. To reiterate the main idea, what we've done is we've generalized the convolution operation to graph structured data. These convolutions, which are motivated by first-order approximations to spectral graph convolutions, can be stacked with intermediate activation functions to form a high-performing model for semi-supervised node classification.